Heart's Delight 46th lecture, and we continue our discussion on widebanding by local feedback, and we will also consider feedback cascades for widebanding. The circuit that we were discussing last time is that of series, and it was simply this: a current source in parallel with a resistance Rs. We have the transistor Q, and there is a series feedback through unbypassed emitter resistance, and no, I'm sorry. What were we considering? We were considering the shunt one, or was it the series one? We were considering the series one. Yes, shunt one we had already discussed. Okay, that is this is the load resistance, and this is I sub O. Because it is series, we have our modeling is also incorrect. It's a voltage source. Okay. You take only the brown line. Rs, we had taken this to be Rs prime, but let's see, this is Vs Rs. We had drawn the equivalent circuit, and the equivalent circuit was Vs Rx prime, which is equal to Rx plus Rs. Then we have a Z pi, which is the parallel combination of R pi and C pi. Then we have Re, which goes to ground, and we have C mu, and a current generator GMV, and the load resistance RL. We had analyzed this circuit for the mid-band gain, and the expression for mid-band gain was GT, which is equal to I0 by Vs transfer. It should actually, okay, mid-band gain. So GT is equal to minus beta 0 divided by R pi plus Rx prime, no 0, plus beta plus 1 divided by R pi times Re. No, not divided by R pi. No division by R pi. Beta plus 1 Re. If it was divided by R pi, it would not have been dimensionally correct. Okay? Alright, so do correct me. We also found out by inspection that the input resistance at mid-band, it's simply Rx prime plus R pi plus beta plus 1 Re. The output resistance, however, did pose some problems. We had to make this calculation, and the exact expression is R0 times 1 plus, this is the expression, Gm plus 1 over R0, 1 plus Rx prime divided by R pi, and in the denominator 1 by R pi plus 1 plus Rx prime divided by R pi multiplied by 1 by Re. This was the exact expression.
Are is the input resistance seen by the source, or what is Re?
Oh, thank you. This dash should not be there. Thank you. It is the resistance seen by the source along with its internal impedance. That is Vs-Rs combination. So this dash shall not be there. R out similarly is the resistance seen by RL, seen by the load, and therefore it does not include RL. Okay. Now the next question is the calculation of FH by the method of, well, we can apply any method, but the method of open circuit time constants. That seems to be quite handy at this point of time. And what we require is an equivalent circuit in terms of its components shown distinctly. we have to calculate this time constant, so we must show the capacitances and the resistances separately. So we have Rx prime, R pi, and as you will see, we will do this by almost by inspection. Okay, you don't have to calculate every time. C pi, Re, C mu, GMV pi, and RL. We have to calculate R pi, two resistances. R pi is the resistance seen by C pi by open circuiting C mu, and the resistance R mu, resistance seen by C mu by open circuiting C pi. In both cases, the source has to be shorted to ground. Okay, let's look at the first circuit. The first circuit, that is the circuit for calculation of R pi. In order to bring the point home, let's spend a little time in drawing the circuit that is seen by C pi. Now, seen by C pi means that instead of C pi, let's include a voltage source V and let the current be I. Let's call it V1 and I1. Okay. So, what it sees first is a parallel R pi and then an Rx prime which goes to ground. The voltage across R pi is V pi, therefore V1 is equal to V pi. Agreed? That identification is easy. Then we have the resistance Re and the current is GMV pi, which is the same as GMV1, and this goes to ground through RL. The first thing, is that clear? Is that okay? We have omitted C mu because it's an open circuit, we have included everything else. The first thing you notice is that the source is in parallel to resistance R pi. So, whatever capital R pi is, it would be R pi parallel some other resistance, let us say R pi prime. And for calculating R pi prime, obviously what you will do is you take this off. Then you see it is a series circuit except for this current generator. But you know what this well, let me draw this circuit. We have Rx prime which goes to ground. Then we have V1, I1, Re, and then RL in series with GMV1 is not effective at all. It's a current generator, and therefore what happens is there is a current GMV1 here. Okay, and by inspection you can see that this current is I1, so this current is I1, so this current must be I1 minus GMV1, and therefore if you write KVL around this loop, you get I1 minus GMV1 times Re. Yeah. Re parallel? No. RL comes here. But since it's a current generator, it's ineffective. Okay? Okay. So this drop plus minus, then you must have minus V1, minus plus, then plus I1 Rx prime. That is equal to 0.
So the current through Rx prime is not I1.
Now it is I1. Now it is I1. Why? Because R pi we omitted. We wanted capital R pi to be, you see, the simplification. These are matters of common sense. If you had included this, you will have to write bigger equations. Okay. What you see is that whatever resistance this source sees is a parallel combination of R pi and some other resistance. It is this some other resistance that we want to find out. So we have omitted R pi. Okay. And from this obviously you can find out V1 by I1, and this comes out as Rx prime plus Re whole divided by 1 plus Gm Re. You have done such exercises in the past, that if there are two resistances in series and one is shunted by a current source, dependent current source, then this is the kind of expression that you get. Alright. So, my capital R pi is now simply small r pi parallel Rx prime plus Re divided by 1 plus Gm Re. Next, the calculation of R mu. For the calculation of R mu, once again no elaborate procedure is needed. All you have to do is across R mu, across C mu, you connect a voltage source. Call this a V2 and let the current be I2. Then what does it see? It sees a resistance R pi across which the voltage is V pi. Then it sees a resistance Re, a current generator Gm V pi. This V pi is related to V2, but we don't know what the relation is. And in addition, now you cannot ignore RL. In addition, you have an RL. And the component that you have missed is that from this point you have an Rx prime to ground. Is that okay? Rx prime to ground. So by inspection you notice what these currents are. What is this current? This is V by R pi plus GMV. V pi. V pi by R pi, and this is GMV pi. What is this current? This is obviously I2 plus GMV pi. Okay. Now if you write a KCL at node N1, if you write a KCL at node N1, then you get I2 as equal to V pi by R pi, this current, plus the current through Rx prime.
So it will not be V pi by R pi.
V pi by R pi plus the current through Rx prime. Now for the current through Rx prime, you require the voltage across Rx prime, which is obviously V pi plus this current multiplied by Re. Alright. So I can write the following equation. I2 as equal to V by R pi plus V pi by R pi plus V pi plus V pi by R pi plus Gm V pi multiplied by Re. This is the voltage whole divided by Rx prime. Okay. This is one of the equations. Now in this equation I don't have V2, so I must write another equation involving V2. Alright, and that equation you have a choice. By choice you may also repeat the same equation. Don't do that choice, okay? Somehow you must involve V2, and therefore the easiest thing to do is to write a KVL around this loop. That will include V2. Wherever you write a KVL, obviously you cannot write a KVL like this because you have a current source, you don't know the voltage across it. So this is a natural choice, and the KVL gives I2 plus Gm V pi times RL, then minus V2, that's right, minus V2 plus the voltage across Rx prime, which is V pi plus V pi by R pi plus Gm V pi multiplied by Re. That should be equal to 0. These are the two equations from which you have to eliminate V pi. Obviously V pi can be obtained from this equation in terms of I2, substitute here. The result is a bit long, but this is the result. R mu comes out as RL plus R pi Rx prime 1 plus Gm RL plus Re divided by Rx prime plus R pi 1 plus Gm Re. One wonders, after obtaining this expression, that RL comes in series. Now in the original circuit we could not identify that. You see, V2 and I2, if RL had come in series, we could as well have omitted it and then added it later, just as we identified a parallel component and we said we will throw this out, we will calculate the rest of it, then parallel it. We could have done that here also. We could have shorted RL. Now tell me, where is the fallacy? Where did we go wrong? RL comes in series, why couldn't you identify it earlier?
So it's not totally in series.
That was an illusion because there is an RL here. It just happens that you can write it in this form. It is not that RL could be taken out or excluded from the circuit because RL comes here also. Wonderful. So once you have calculated R pi and R mu, your FH is only simply twice pi R pi C pi plus R mu C mu. Let's consider an example and see how things improve by means of this series feedback. We take an example in which RS is 500 ohms. Small Rx is 100 ohms. I have intentionally taken this to be a large figure so that it becomes comparable to capital RS. R pi is 1K, a good figure. C pi is 20 puff. Re is 1K. RL is 5K. C mu is 1 puff, so a good transistor. Gm is 0.1 mho, and obviously beta, since R pi and Gm are given, beta is 100. I calculated the components R pi and R mu under two conditions. Have you taken down? Okay. Under two conditions, that is two values of Re in K. One is 1K, the value that is given, and the other is 0. That means there is no feedback. No feedback. I calculated the time constants R pi, C pi, R mu, C mu for two conditions. One is for the given condition, that is Re equal to 1K, where there is feedback, and Re equal to 0 where there is no feedback, or Re is simply bypassed through a capacitor. I calculated them and the values are the following. Please do verify them. I found that this is equal to 0.016K, so it's simply 16 ohms, very small value, and R mu is 5.6K. Then FH under this condition in megahertz comes as 26.9. 26.9, and with 0 R pi comes as 1K, R mu is 187.5 K, and FH comes simply as 0.77. And you see the order of improvement in FH. I would also like the question, is this a fair comparison? No, because we have not kept the gain constant. The gain is affected, but that's a fact of nature. You can make up the gain by some other means. I'll give you a tutorial problem in the tutorial, next tutorial sheet, the last one. Now we have considered these two examples of local feedback. One was shunt, and the other is series. There could be other examples also. Now in shunt, what are the characteristics? Input resistance low, output resistance low. And in shunt, what is the basic amplifier? Voltage to voltage or voltage to current or what? Current to voltage. Current to voltage. Okay. So I to V. It's a current to voltage transducer. What is it called? What is the name? CVT. Okay. Current to voltage transducer. In series, Ri is high, R0 is also high, and it is VCT. That is voltage to current. Don't you see that they are complementary? CVT and VCT are complementary. And if you have to cascade two gain stages to increase the gain, the natural choice would be to cascade a shunt to a series. Either way, either shunt first and then series, or series first and shunt later. Let's consider these two examples.
What is the criteria for
I'll tell you what the criteria is. Which one should come first? All right, let's discuss the criteria. Suppose you want to increase the gain. You have designed these two blocks, but individually they are not adequate as far as gain is concerned. Okay, what would you do to increase the gain? Of course, if you cascade two stages, the high frequency 3 dB cutoff is also going to increase or decrease? Decrease. There is always a shrinkage. Whenever you cascade, the bandwidth always shrinks. But nevertheless, maybe you overestimate, you overdo this. That means if you want an FH of 1 megahertz, maybe you design this for 20 megahertz. And similarly, this one also for, let's say, 15 megahertz. Then you combine the two, you will surely get 1 megahertz. Okay, so you'll have to design. But in the process, you have reduced the gain. When you cascade the two, the gain shall increase. But what would be your choice? Suppose I cascade shunt, then series. What would it be used for? Current amplification. Because in shunt, the input is a current, and then if you use a series, the output is a current. So it is a current to current. And this is a good match, good combination, because the output impedance of the shunt is low. Output impedance is low. What is its output? Output is a voltage. And therefore, to the series, you have put a voltage source. Okay? That's what it wants. And then its output impedance is high, which means that the output behaves as a current source. So this will be, if you say shunt followed by a series, this would be a current to current amplifier, a current amplifier. And there's good matching, you don't lose anything in the interfacing. Okay? You have connected a low impedance output to a high impedance input, so that you make sure that the total voltage, there is no voltage attenuation in the interfacing. Okay? On the other hand, if these two are interchanged, then it's a voltage to voltage amplifier. Let's draw this to make an imprint in the mind. I will draw the series first, then shunt, which will obviously be the dual of this. That means it will be a voltage amplifier, voltage to voltage. So series, which means that you have a Q1 and RE, you have an RL1, and then the output of this, output impedance is high, so the output of this will behave like a current source. So it is this current which is our concern, and this current is fed to the second stage Q2, whose emitter is grounded. It has a resistance, let's say RL2, and this is the shunt feedback RF. The output of this would be a voltage V0. Okay, it's a voltage to voltage transducer. You have actually used as VCT and then a CVT, and the matching will be perfect here because the output impedance of Q1 is high. This is the natural choice for cascading. Now you can show that V0 by Vs, if beta is high, can you guess what this would be? You see, I1 by Vs, what is the value? Approximately beta is high, if the pardon me? No, no. It is the current to the voltage. It is not minus Gm V pi RL. I am not taking the voltage. I am only taking minus Gm V pi. Now, the you see, if you take the voltage here, then what it says is correct. This voltage to this voltage will be approximately RL1 by RE. But if I take the current here, then what would be the gain? No. Let me repeat. This should be obvious. This voltage to this voltage is approximately minus RL1 by RE.
1 by RE.
That's right, minus 1 by RE. Okay, minus 1 by RE. We also showed. Pardon me?
I1 by Vs is minus 1 by RE.
That's right. Therefore, I am going to multiply this by V0 by I1. V0 by I1, we showed that if beta is high, then this is approximately minus RF. That's all, nothing else. And therefore, this is equal to RF by RE. Approximately. This is the mid-band value, and that is how one estimates the gain that you will get from this stage. And you see the gain, if the transistors are good transistors, then the gain is controlled by two external resistors. Alright? Of course, choice of these external resistors, do they affect the high frequency cutoff? Sure enough. RE does enter into the FH of this stage. RF also enters into the FH of that stage. Right? So what you have to do is you have to make a compromise. You have to find out RF and RE such that the required gain is satisfied and the required FH is also satisfied. Now let's continue this analysis of this by inspection. Again, you see the two stages, the gain is obviously the two gains multiply each other because there is matching. One is voltage to current gain, and the other is current to voltage gain, and therefore the gain would be voltage to voltage, it would be dimensionless. But nevertheless, the overall voltage gain S sub V j omega, can you tell me the general form? It would obviously be AV J0, that is the midband value, divided by 2 poles. Actually there would be 4 poles because each transistor contributes to 2. But we have employed the method of open circuit time constants to determine an effective FH, and therefore what we will have is 1 plus j omega by omega h1 multiplied by 1 plus j omega by omega h2. Is that clear?
Where omega h1 and omega h2 are the corresponding cutoff frequencies
of Q1 stage and Q2 stage.
individually.
That's right, individually. And if you want to find out the overall cutoff frequency, obviously the relationship would be that omega h squared divided by omega h1 squared. You can find this out exactly, isn't that right? You can find this out exactly. Let me give you the omega h1 is the cutoff frequency of this stage, the first stage, and omega h2 is the cutoff frequency of the second stage.
While they are a part of this whole system.
While they are part of this one, because we have taken care that there is matching here. Okay, that the output of this behaves like a current source. So they multiply. Okay. Now, since this is, we don't require any more approximation because this is only a quadratic. Let me give you, it would be instructive to derive this formula. I have done that. FH is equal to exact formula. However, FH1 and FH2 are not exact. They were obtained by approximation. Okay, but nevertheless, after that you don't need to make an approximation because it's a quadratic and you can solve it. My solution is this: minus FH1 squared plus FH2 squared. Please see if this is correct. Actually, there would be a plus minus, but the minus sign won't give you a positive value. So you have to take FH1 squared plus FH2 squared whole squared plus 4 FH1 FH2, this whole thing to the power half. Agreed? That is the result.
So it
See.
should be 4 FH1 square into FH2 square.
That is correct, absolutely correct. I stand corrected. On the other hand, if I do it the other way around, that is shunt, and that is followed by series, my circuit would be like this. Now, I must work with a current source because I have a shunt, and we may include an RS, we may not include an RS. All right, let's include an RS. Did we include an RS in the previous case? No. Then let's forget it. After all, that will come in parallel with R pi anyway. Okay. So this goes to ground, and I have a resistance from here to here, RF. I have an RL1. Now this goes to the second stage, Q1, Q2, in which there is feedback through RE, then RL2, and the output is taken here. Not quite. Output is taken as the current in the load, because this will now be a current to current amplifier. The output impedance of Q2 is low, isn't it right? Low or high? It's high. That's why the output is a current source. Okay. So this is a current to current transducer, and you can see that there is matching at the interface. That is, the output impedance of this is high or low? It's low. That's why this voltage, let's say this voltage is V1. V1 by Is would be approximately equal to what? If beta is high, V1 by Is would be approximately equal to minus RF, and I0 by V1 would be approximately equal to minus 1 by RE, and therefore I0 by Is at midband would be approximately equal to RF divided by RE. Once again, the current gain is controlled by two external resistors, and here also one can find out the effective cutoff frequency. Now, in practice, which of these do you think would be more popularly used, more commonly used? You see, somehow or other, because of history of electronics, voltage processing is still, people are comfortable with voltage processing, and therefore voltage amplifiers are mostly used. Current amplifiers, unless the situation so demands, one tries to avoid. But this is purely a mental bias. There is no reason why current processing cannot be done as comfortably and as easily as voltage processing. And therefore, in most of the practical circuits, practical instrumentation circuits and all that, what you get is this circuit, a series followed by a shunt, the voltage amplifier. Sometimes, yeah.
In all these circuits, we have balancing resistances.
Of course, that we have not shown.
Yeah, but we should have included that in the equivalent circuit, because can have a shunted RB.
Or that RB, we ignore it. Or we say it has been done by current source. Anyway, if it is to be cheap, it has to be done by current source. Okay? And therefore, that shunting effect doesn't come. If it's a discrete circuit, then you make sure that that RB does not load the effective resistance between those 2 points. Okay? Now, sometimes you will see in practical circuits, if you open a chip or take the circuit in the application note, you will see that there is a third transistor here. Can you guess what the reason is? It is followed by a third transistor, which is non-feedback.
To increase the current output.
To increase the current output. This is a voltage amplifier. Why should I increase the current output?
Fan out criteria.
No, that's not it. It's simply another buffer, another common emitter stage. Another common emitter stage, so that if you connect a source here, you see, even with this, the output impedance is not zero. Isn't that right? We calculated the typical value was 234 ohms or so. Suppose you have to drive a loudspeaker. Then obviously 230 ohms of output impedance is not good enough. It's very high compared to the loudspeaker impedance of 8 ohms. And therefore you have to use a third stage, a buffer, whose output impedance is of the order of 1 by Gm. Okay? And therefore you have to choose the operating point of the buffer such that 1 by Gm is negligible compared to the speaker 8 ohm impedance.
Excuse me, sir.
Yeah.
So FH for these two circuits will be the same.
FH for these two circuits will be approximately the same. Approximately the same. Now, the next point for consideration is, what about overall feedback? These are local feedback cascades. What about overall feedback? That is, 2 or more stages, and then you bring feedback into consideration, feedback connection. As I said, the problem is that it's more difficult to adjust. Isn't that right? You have a couple of stages. The feedback is around the overall loop. It is difficult, is more difficult to adjust. Whereas in a cascade, you can adjust, you can design the each stage independently and then cascade, making sure that matching is obtained. So overall feedback, there is a problem of individual adjustment. There is also a problem of stability. In an overall feedback circuit, 2 or more stages, this is more prone to instability than local feedback stages. Nevertheless, overall feedback is used because of different reasons, because of the ease with which it can be done. Suppose individual stages have been designed. People have spent, let's say, 30 engineer hours to make a good amplifier. And then suddenly you find that that much of gain is not needed. Because if that gain is there, your bandwidth is less than what is desired. So the simplest thing you do is put a negative feedback, reduce the gain, that will increase FH. Okay? So overall feedback should also be considered. However, because of stability problems, the number of stages in overall feedback is restricted to either 2 or at the most 3, not more than that. Okay? 2 or 3. Let us see a typical configuration. If it is 2, then it's called a feedback pair. This is the, the Americans are very good at coining names. Whatever you make, they'll give a name. It's called a feedback pair. And the chip will be called a feedback pair. I mean, you'll have to go and ask for the number, and the numbers are so close together, any 555, any 556, they could be quite different chips. You'll have to say feedback pair. If it is 3, then it's called a feedback triple. Okay? What is it called if there are 2 children of identical twins? Okay. I'm glad they didn't call it feedback twins, because they are not twins. They didn't call it feedback triplets, they simply call it triples, feedback triples. Now, let's look at a typical circuit. Okay, if you have a let's see, we have a 2-stage amplifier, let's say. RL1, this goes to the second stage, Q2. I am not showing the other connections intentionally, and this is your output. And you suppose you want to make a series shunt, then obviously it's a two-stage amplifier. So what you will do is, normally this will go to ground, this should also go to ground if it's a simple two-stage. So what you do is you connect a small resistance here, RE, and then connect this to RE. Straight away? No, through a resistance, let's call it R. So this is a series shunt configuration. It's a cascade of two stages, and this is an overall feedback. There is no local feedback. The feedback is through RF. Okay? If RF is cut, then there is local feedback. But if RF is not there, RE shall also be made equal to 0. Okay? And you can show, now what is this stage suitable for? Obviously from the variables that I have written, obviously it's a voltage amplification. But why? The input impedance here is high. Isn't that right? Because of series feedback. And the output impedance is low because of shunt. And therefore it is suitable for voltage to voltage transduction. Okay? And you can show that A sub V, can you guess what the value would be if the transistors are good transistors, beta is high, then it is, no, it is RE plus RF divided by RE. RE plus RF divided by RE. That means it is 1 plus RF by RE. Compare with a non-inverting op-amp connection. Okay? It compares very favorably with that. And on the other hand, if we have, let's say, shunt series, if we have a shunt series, then we shall have a circuit like this, Q1 shunt series. So the connection is from here, RF, RL1, this goes to the second transistor Q2, and a resistance RE, RL2. Has it become a shunt series? Yes, this is series and this is shunt, right. Obviously the input impedance now would be low or high? Low. And therefore the appropriate source to be applied is current source. And therefore the appropriate output to be taken is a current. No, is a current. The output impedance is now high, and therefore it behaves like a current source, and therefore it's a current to current transducer. And you can show, please do show, that this gain formula is the same, 1 plus RF by RE. This is of course the mid band gain. The calculation of FH is now not as simple as the feedback cascades. The calculation of the upper 3 dB point, you shall have to draw the overall equivalent circuit, and you shall have to apply the method of open circuit time constant. There is no other way. And you agree that if even in 2 transistors there is no other way, because you will get a 4th order transfer function. 2 capacitors here, 2 here, minimum 4th order. In addition, if there is a load capacitance also, then of course you are sunk. There could be a capacitance here also across RE. Okay? And therefore the method of open circuit time constant is the only thing that, and in 1 or 2 of these it would be instructive if you do carry out this calculation. That's all for today.